This is assignment 2.3 on fatigue and recovery. So fatigue is extreme tiredness resulting from mental or physical exertion or illness, and so anyone can experience fatigue for a number of different reasons. However, fatigue is particularly relevant during sports. Different sports could be more or less likely to induce fatigue. It is dependent on a criteria such as the intensity, duration, energy systems, fuel, waste products, muscle fibers used, and whether it is continuous or intermittent. There are 3 different types of fatigue: local, general, and chronic. Local fatigue is where the fatigue is localized in the muscle used from repeated contractions without recovery. General fatigue, for example, is how you feel post-training or game, where you feel physically or psychologically weak. Chronic fatigue is where a person experiences a weakened immune system from excessive overtraining and inadequate recovery. Some symptoms of fatigue are muscle pain, burn or heaviness due to a build-up of lactic acid and depletion of glycogen stores, lightheadedness due to a lack of oxygen and blood to the brain, which also causes cognitive function to decrease and a person will make bad decisions in a game. Prolonged exercise in hot conditions where a person becomes dehydrated can lead to muscles cramping up, and there can also be a feeling of general tiredness. There are different causes of fatigue. Increased acidity due to a build-up of lactic acid causes the enzymes used for resynthesizing ATP to denature, which means a person has less energy and feels fatigued. A person's phosphocreatine stores decreasing can also lead to fatigue. Alternatively, a lack of food fuels such as carbs, fats and proteins can also lead to a person feeling tired. There are also ways in which you can delay the onset of fatigue, such as energy gels and energy drinks to replenish glucose stores, carb loading, a method used by endurance athletes to increase their carbohydrate stores before their event, and working under their lactic acid threshold to avoid the build-up of lactic acid in their muscles. The more intense an exercise was, and the more a person's glycogen stores have depleted, the longer it will take for them to recover. There are such a thing as overtraining, exercising beyond the normal physical tolerance limits when the body is unable to recover adequately during the rest periods. There are different symptoms and effects related to overtraining, such as tiredness, poor motivation and sleep problems, hormone imbalances, muscle and skeletal tissues being unable to repair, poor or inconsistent standards, and a person being more susceptible to injury and illness from a poor immune system. There are different causes for this as well, such as pressure from coaches or parents, an addiction to exercise, imbalanced training program, or just a lack of knowledge. Maximal intensity exercise, which lasts for a very short duration, uses the ATP and PC systems, both of which are anaerobic. This is because the actions only last a very short period, no longer than 10 to 15 seconds, and they involve exerting maximum force, which can only be achieved by the ATP and PC systems, as they are such simple reactions that produce large amounts of force. There are no waste products when using these systems, and it involves recruitment of fast glycolytic muscle fibers, as they are able to produce the largest force in the shortest amount of time. However, this does mean they fatigue quicker. As there is a limited store of ATP and PC in the muscles, and these systems only use ATP and PC as fuels, the ATP and PC stores will deplete quickly, as they have also yet to be given time to recover and resynthesize to replenish their stores. This means that they can't maintain the high level of intensity for very long within their performance, hence why the system is only used for very short duration events such as discus long jump and 100-meter sprint. In discus, they would only use the ATP system as their fuel, as it lasts no longer than 3 seconds, and as it uses ATP, there are no waste products. However, in an event such as 100-meter sprint, the ATP stores will deplete and a different energy source will be recruited, which is the PC in this case. It's possible for athletes who know they rely heavily on their ATP-PC system for their event to take creatine supplements in order to increase their body's stores of PC, which will enable them to keep going at such a high intensity for a longer period of time, which may give them the edge over their opponent. Moderate intensity and moderate duration activities such as the 400-meter sprint event will use their ATP-PC system, but predominantly use their lactic acid system. This system can last for around 3 minutes, which is because it produces lactic acid, a waste product that can inhibit the enzymes needed for respiration and stop them from doing so. The lactic acid build-up causes the acidity to increase and therefore the pH levels to go down, which can cause cramping and stiffness within the muscles. This system also uses carbohydrates as its source of fuel, which is then converted into glycogen and glucose, and during the anaerobic process of splitting glucose down, ATP is made. And so as a person works within the lactic acid system, their glycogen stores will deplete greatly, as this is the only source of fuel it can use. There is no other fuel that it can deplete, so it has to be the glycogen. As a person works using the lactic acid system, it can cause a build-up of hydrogen ions to occur. This is the acid part of the lactic acid, and it interferes with the electrical signals in your muscles and nerves, which slows energy reactions down by inhibiting the glycolytic enzymes, and therefore impairs muscle contractions. OBLA stands for the onset of blood lactate accumulation. This is the point at which the lactate levels in the blood become too great and begin to have a negative impact on performance. It typically happens when the blood lactate level reaches 4 millimoles. However, athletes can train to delay the effects of OBLA so that their body can keep going for longer before the lactate levels become too much. Also noted on the graph is the lactate threshold. This is the point at which exercise switches from the ATP-PC system to the lactic acid system. One way in which a person can delay the effects of fatigue associated with the use of the lactic acid system is through the use of glucose ingestion. By taking more glucose, it means there is a bigger fuel source, and so they can go for longer before all of their glycogen stores deplete. Submaximal intensity events such as marathons and triathlons will predominantly use their aerobic system for the majority of the event. However, the ATP, PC system and lactic acid system will be used at certain points as well. As they're using the aerobic system, they will rely heavily on the glycogen stores, which come from carbohydrates as well as their fats. In extreme cases, muscle proteins can be used as fuel too. As a result of using their aerobic system, they'll produce a few waste products: water, heat and carbon dioxide. Glycogen can be broken down in aerobic respiration to create ATP, the energy needed to sustain exercise. Alternatively, the body can break down fats to produce energy. Breaking down fats produces more energy than the carbohydrates. However, it requires more oxygen to do so and can take a much longer period of time as opposed to breaking down the glycogen. By using fats as opposed to glycogen for long duration events, it means that a person can keep going for a longer period of time. Once a person's glycogen stores deplete completely, they are essentially done, so by burning fats instead of carbs, they are allowing themselves to keep going for longer. The waste product, water, is removed from the body in 3 different ways. It can be breathed out as water vapor, got rid of through urination or sweat. CO2 can also be removed in three main ways. 70% of it is removed in carbonic acid, 23% as carbaminohemoglobin, and 7% is dissolved into the plasma. CO2 dissolves into the red blood cells, then the carbonic anhydrase converts the CO2 into carbonic acid. Some will bind with the hemoglobin to form carbaminohemoglobin, then the rest just dissolves into the plasma to be carried away in the blood. The complete depletion of glucose stores can cause a person's body to essentially shut down, as they are no longer able to produce any more energy, meaning that their muscles can no longer function properly. However, some athletes are able to train their bodies to use fats as a source of energy whilst using their aerobic systems over using their glycogen stores, which means that they can preserve their glycogen stores to use at a later point. This is called glycogen sparing. Alternatively, athletes taking part in long-duration submaximal activities might choose to take on glucose gels during their event to top up their glycogen stores, which were depleted during the event, allowing them to go on for longer. Or they might try carbo loading. This involves a person first depleting their glycogen stores around 7 days before their event by exercising lots to use up the current stores of glycogen they already have. They also make sure they don't consume any carbohydrates in their diet. Because of this, the body begins to panic that it hasn't got any glycogen, and so the next time it gets some, it grabs hold of it and stores it. At this point, a few days before the event, the athlete consumes lots of carbs, and the body stores all of this as glycogen, which results in the body's store of glycogen increasing from what it was before they began the carbo loading process. In an intermittent activity such as football or rugby, all of the energy systems will be called upon at different times. For example, in football, the ATP system would be used for quick actions such as striking the ball for a penalty. The PC system would be used for a short for short, sharp runs, and the lactic acid system will be used for more prolonged periods of running, such as a player on the wing who has just run up the pitch on the attack and then having to get back to defend on the counter-attack after losing possession of the ball. The aerobic system would then be used at calmer points of the game, such as the players getting set for a goal kick or corner. As it is using all of the energy systems, all of the previously mentioned fuels will be used, glycogens, fats and sometimes proteins, and again, because all of the systems are being used, all of the previously mentioned waste products will also be left around: heat, water, CO2 and lactic acid. In order for muscles contractions to occur, calcium ions need to be released from the sarcoplasmic reticulum, which occurs after a nerve impulse is sent down a motor neuron. The ACH chemical is then pushed across the synapse so that the impulse can continue to the muscles. However, if there is a depletion in the ACH and not enough is pushed across the synapse, then the contraction will not occur, in which case the enzyme choline something then removes the excess ACH that was left in the synapse to make way for the next contraction. When discussing the recovery of these activities, there are certain parts that should be looked at with regards to all of them. O2 deficit and EPOC. O2 deficit is the oxygen that you would ideally need for the activity but don't necessarily have access to, and this would vary depending on the activity. EPOC stands for excess post-exercise oxygen consumption, sometimes referred to as oxygen debt. The extra oxygen the body has to take in after finishing exercise to recover effectively. The oxygen used above resting levels during recovery. EPOC can be split into three different phases: alactic fast recovery, lactacid slow recovery, and metabolic needs. The alactic fast recovery phase happens immediately after exercise and involves using the oxygen in order to restore ATP and PC stores. The lactacid recovery is primarily to remove lactic acid from the body, deal with CO2, and it does this in a few ways. 65% of the lactic acid is converted into pyruvate, which then enters the Krebs cycles and is eventually converted into CO2 and water. 20% of lactic acid is converted into glycogen in the liver and then stored in the muscles and liver through the Cori cycle. 10% is converted into protein, and the last 5% is converted into glucose at the liver and used to then make ATP. Metabolic needs includes the energy needed by respiratory muscles during the recovery to sustain a higher heart rate and breathing rate to essentially repay the oxygen debt. In maximal exercise, it doesn't take very long at all to recover from the intense activity, roughly no more than around 5 minutes to fully recover. During maximal intensity exercise, the O2 deficit is larger as no steady state is achieved, and consequently, because the O2 deficit is larger, it means that the EPOC is also larger. In this one, only the alactic recovery is really used for the resynthesis of the ATP and PC stores, as they were the only ones used. However, the hemoglobin and myoglobin are also once again saturated with oxygen, which takes around 1 to 2 minutes until they are fully recovered. For moderate intensity activities such as the 400 metres, it will take roughly 2 hours to fully recover. There will be a slightly smaller O2 deficit in this case, but steady state will still not be reached, and so the EPOC will still be fairly big to match the O2 deficit. In this case, however, all three phases of recovery, alactic, lactacid, and metabolic demands, will be included within the EPOC. This is because the alactic needs to replenish the ATP and PC stores from the usage of the ATP-PC system, and the lactacid is needed to remove the lactic acid that will have built up as a result of using the lactic acid system. The varying percentages of lactic acid, as mentioned before, will be converted to glucose, protein, and pyruvate. In addition to this, the metabolic demands will be included because they will have been working long enough to justify it. They will need to keep their breathing rate and heart rate up slightly longer as they need to take in more oxygen. Another aspect related to moderate intensity exercise is DOMS, delayed onset of muscle soreness. This is caused by myofibril tears in the muscles from eccentric and unaccustomed exercise. It triggers an inflammatory response which includes swelling, altered muscle firing patterns, and pain 24 to 48 hours after. It causes muscle strength and motion to be impaired. Submaximal events typically have a smaller O2 deficit as they reach steady state exercise and the process is mostly aerobic, therefore less lactic acid is produced. As there is a smaller O2 deficit, that epoch is also smaller. As they have consumed less VO2, they are able to technically repay their oxygen debt back quicker. However, in terms of replenishing glycogen stores, this can take days. Within the epoch of submaximal exercise will be all three phases: alactic, lactacid, and metabolic demands. In addition to this, there are other ways in which we can speed up the process of recovery, such as foam rolling and massages, ice therapy. It's the white blood cells that cause inflammation, and ice therapy shrinks the blood vessels and slows down the release of white blood cells, which therefore puts the muscles in a better state, ready to work again. There's also contrast water therapy, which involves moving from hot to cold water, and active cool downs.